Welcome everyone to session 1C. Today's topic is on determining limits. So in our previous video, we worked with estimating limits through tables and graphs, but here we want to have a faster way that uses just algebra to quickly determine the limit using just the algebraic expression. And now at the heart of this are the properties of limits. So if we take the limit of f as x approaches c to be L and of g to be m, then we have all of the following limits. So all of these are true, and all of these are really just really intuitive. And if you look at them, for example, the limit of a constant is a constant, limit of x as x approaches c is c, the limit of the sum is the sum of the limits, the limit of the difference is the difference of the limits, and if you have a constant, you can pull it out, sort of. So if you have, if you want the limit of a constant times a function, it's just equal to that constant times the function's limit. If you want the limit of a product, it's just the product of the limits, and if you want a limit of the quotient, then it's just the quotient of the limits. And this would also work for exponents. So if you want the limit of a certain function to a certain power, then you can simply take the limit of the function at that value to that power. So all of these, if you don't get immediately, it's fine, and you don't really have to know how to prove it because using that requires delta epsilon, which isn't required in AP in the first place. But again, all of these are highly intuitive, and you can really take them for granted for a course like AP. Now, a consequence of all these properties is that virtually any function composed of plus, minus, times, divide, or something like a power, so power, and if you have a constant, anything composed of these operations, let's say f of x, then you can sort of distribute the limit in. So there's a certain intuition that you could distribute in the limit. And to illustrate this, for example, if we have f of x, let's say for something easy is x squared plus 2x plus 3, then what would happen is that the limit would sort of distribute its way in. So if you have the limit as x approaches c of f of x, then this is just equal to the limit as x approaches c of this whole thing in here. And then because you can treat, let's say, x squared as an f, this as, or like this latter part as a g, then the limit of a sum would be equal to the limit, the sum of the limits, and that you can rewrite as x to c of f, which is x squared, plus the limit of 2x plus 3. And you can keep breaking it apart until you have each of the terms. And let's say for this x squared here, we have x times x, and that would be the limit as x approaches c x multiplied by the limit as x approaches c of x, plus here we can break it apart again, 2x, limit of 2x plus limit of 3, and then we can, because by the constant property, we can pull out the 2, and we can find, and then we can find the limit of 3 as x approaches 3. And so for each of these individual elements, we're getting narrower and narrower in terms of the limit, and then ultimately we would evaluate all the x's by the c's. So it would look something like this, and ultimately we get the exact same result as we would by just directly plugging the c in. So for most cases involving these operations, we would have that this limit as x approaches c of f of x is equal to f of c. And you can really get an intuition for this by taking many functions and breaking them apart like I did using these properties to ultimately find the same results. So this is why properties of limits is at the heart, because it allows us to directly find the limit by plugging in the value. And later, this property will be known as continuity, as we will explain in the next video. But this is a good foreshadowing. So some examples here, if we treat this 5 as a function, then if we just plug x equals 2 in, then that's just going to be 5 itself. So this is the idea of substitution. So we're going to use substitution to evaluate all of these really easily. So -1 as x, so you get -1. Here you plug in x equals 3, that's 7. Also, by the way, feel free to try breaking these apart. These are all helpful examples. But here you would just do 1 minus 4 plus 7, and that is equal to 4. Here, we plug this in, we would find that the first factor is 0, so it's just 0. Here, we have, if we try to directly plug this in, that the numerator would give us 0, and the denominator would also give us 0. And this is what we call the indeterminate form. And this is a big uh-oh for us because it means that we need further steps to deal with this, and we'll cover 2 of the big methods later in this video. And here I would like to briefly add an example here. Let's consider this simple limit as we have seen in the last estimation video. And what our conclusion from the video last time was plus or minus infinity, aka it does not exist. And here I'm going to show you how this result can still be obtained, because when we plug x equals 0 in, we would get 1 over 0, and this would directly lead to does not exist. And the general procedure is that whenever you see through direct substitution that the result is b over 0 for b is not equal to 0, then we conclude that it is a does not exist. So this is perfectly valid and the standard solution for questions like this, where the limit is undefined. So you write does not exist. Okay, here we can still keep substituting. So you just plug x equals 3 in. This would give you 1 over 16. Here you can plug in x equals 1, this would get negative 1. Just as an example, I'm going to show you how to distribute the limit in. So here what we could rewrite this as is x minus 2 to the 1/3. And then what you can do is you can pull this 1/3 exponent out per the properties of limits like this. And what then you're going to get is that you can evaluate this part, or you can further separate that, but I'm not going to do that here. And that's going to give you negative 1 to the 1/3, and that's going to give you negative 1, as we have here. Here, we can just keep plugging in. This is going to give you cosine pi, that's going to be negative 1 squared, minus 2 sine pi over 2, that is going to be 1. So this is going to be negative 1 altogether. And here you might ask why we can directly use a substitution for cosine and sine. And there are 2 ways I can explain this for you here. One is just through the graph. If you observe the trig graphs, you would find that they are somewhat continuous. And what this means is that the point that its limit gets to is just equal to the point itself, which is what we're doing here for the direct substitution. Now, the second way I could explain this is just by continuity, which we'll cover in our next video. And hopefully here, this has already developed an intuition to a certain extent. Of course, you don't have to know exactly what it is, but we'll show what type of functions we could use this property for in general. And this is what we call continuity. So here is our first method overall. It's just by substitution. You just plug in f of c to find the limit as x approaches c of f of x. And so the only problem that we would have here is if we get something like a 0 over 0. And this is the indeterminate form as mentioned, and this is the case that we're going to deal with in the following 2 methods. So the first one is the squeeze theorem. And what it states is this. So let's say we have some neighborhood around x equals a. Neighborhood just means some interval around. It's fairly arbitrary. But here we have 3 functions. We have f, we have h, and we have g in the middle. So by in the middle, we mean it satisfies this property for all values of x in the neighborhood, but not necessarily for a itself. So for everything except a, we have that h is greater or equal to g is greater or equal to f. And what this says is that if the limit as x approaches a of f is equal to L and of h is also equal to L, so h and f converge, or sorry, have the same limit at x equals a, so let's say they're both L, then G would be forced to have the same as well. And the reason here that it does not have to be equal to is, again, that the limit does not concern what the value itself. So it's all about what happens next to it. And really, this is just highly intuitive because G is sandwiched. So this is the other name, sandwich theorem. G is sandwiched between H and F, and so therefore its limit would have to agree to the other ones because it's squished to that point. And the number one classic example of this is sine x over x as x approaches 0. And notice that if we run a direct substitution, this would yield a 0 over 0. So this is an example of us trying to solve the indeterminate form. And to show that this is equal to 1 in the end, we just have to prove the inequality that cosine x is less than or equal to this expression, and this is less than or equal to 1. Oops. And the proof of this is a geometric one, and you can find this all over the internet. And really, though, as x approaches 0, we have that this and this both approach to 1. And so sine x over x is squished to the value of 1. Here, we can utilize the nice property of sine of having the range of -1 to 1. And so we would find that whatever's this expression here is squished between x squared and negative x squared. And as x approaches 0, both sides would become 0, and hence this expression would be equal to 0. Now, using this first classic example, we could solve extensions 1 and 2, and this is a nice exercise for you guys. And so we're going to move on to our third method, which is equivalent forms. Now, the idea of this is to either factorize and then cancel factors, or to use trig identities to simplify. And this often also involves canceling. So we're just going to jump straight into examples. So for example, here, both the numerator and the denominator evaluate into 0 over 0. But what we could do is we could write this into an equivalent fraction like this. So we can multiply both numerator and the denominator by x minus 1. And this would give, here this would give x, and so we can cancel the x with this x. That would give 1 over x minus 1. Here, as x goes to 0, we have, through direct substitution, that this is equal to -1. And so notice that after rewriting into an equivalent form, so this is our final equivalent form, we go back to substitution of the value, because they are equivalent, and so its limit is equal to this limit, and that is equal to -1. So for our next one, sort of the instinct would be to multiply by its radical conjugate, or its radical conjugate's negative. Here, I would just multiply by this over here, and this would give limit as x approaches 1 of x minus 1 over 1 minus x times root x plus 3 plus 2. And this would cancel to -1, and so you can safely plug this in and obtain -1 over 4. Now here, this is a super classic example. This would just be equal to this limit of x to 1, and the numerator we can factorize, the denominator we can factorize, like this, and you can cancel one of the factors, and this factor is causing the problem. So here, now we can safely evaluate this to a 4 over 2, or just 2. Now we have a couple of trig examples. Again, the goal is still to stop the fraction from being a 0 over 0, and the way to do this here would be to rewrite this into 1 minus 2 sine squared theta, and we can take a difference of squares from this. Oops, take a difference of squares from this, so that one of this factor here can cancel with the numerator and leave a root 2 on there. So this would be equal to the limit as theta approaches -pi over 4 of root 2 over 1 minus root 2 sine theta. And now we can safely plug in this -pi over 4 into here, and to ultimately yield root 2 over 2. Now, using the same sort of idea, what we can do for this one is we can rewrite root 3 over 2 into sine pi over 3, and we can rewrite 1 over 2 cosine into cosine pi over 3. And then we can use a difference to product to rewrite both the numerator and the denominator, and then ultimately one of the annoying factors will cancel. So notice in every case we have this annoying factor that causes the 0 over 0 because that same factor evaluates to 0 on both sides. And so canceling that would end up with a really nice expression that we can evaluate. So for this one, I'm not going to run through all the algebra because it's very time consuming, and it's a good exercise for yourself as well. So 6 and 7 are the same type, and we'll still leave these as exercises. Okay, so finally we get to selecting procedures for determining limits. And as we mentioned, the first thing we do is to substitute because it's the easiest. And from this, it's very likely that you'll be successful immediately. If you have something normal, then that's your answer. If you have b over 0 where b is not equal to 0, then we have does not exist. So this is a positive or negative infinity, and we, for calculus here, just use does not exist. Now, the trouble case is the 0 over 0, the indeterminate form. And for this, we described two ways in which we can deal with this. One is the squeeze theorem, and the other is to rewrite into equivalent forms. And specifically, the squeeze theorem helps you squeeze the value into something specific using other functions, while equivalent forms helps you rewrite the expression itself into something that is directly substitutable. So for equivalent forms, you would want to go back to substitute. And later, we will talk about this other method, and it's called the hospitals. And what's really nice about this is that you can do something that's really easy on both the numerator and the denominator, and it doesn't require as much thinking and problem solving as the squeeze theorem or equivalent forms. And for most AP students, this is probably their favorite rule. It's called the hospitals rule. But we'll cover that later, and we'll be sure to let you know of it. So overall, this is the procedure for selecting the method for determining limits. And this is pretty much all that the AP requires you to know on the test. So thank you for watching this video. In our next video, we'll be talking about continuities and discontinuities.